Okay, welcome back, everybody. Appreciate the core of people who continue to come to lecture. I hope you're getting something out of it. I believe you should be. I put a lot into these things and they've been refined over the years. And it's sort of the best of these metrologies that I've sort of compiled information about that are very near and dear to me. And a lot of it's from personal experience working with them. So it's not like I've read some book and I'm regurgitating stuff to you guys. It's stuff that really speaks to the guts of how these things work. And my goal is not to hope, or I don't sit here hoping that you're going to remember all these mathematical derivations, but I'm hoping that you come away with the big picture of how these metrologies work so that you are a more intelligent engineer in the course of your career. I would be perfectly satisfied if the only thing that you benefited from these lectures was the ability to be able to sit in a meeting as a professional engineer and have others talking about strain gauge data, laser vibrometer data, digital image correlation based data, and you not sitting there like a deer in the headlights asking, what is that, right? I want you to feel like, okay, I'm empowered. I understand. I could ask the right questions. I could ask intelligent questions here. And I can at least put a sanity check on what these people are presenting. I know what right questions to ask, okay? That is someone who's more empowered, okay? As opposed to just trusting what's being thrown at you, okay? And oftentimes the people who are presenting this stuff know what they're talking about, and I'm not suggesting that you rip holes in their presentation, but it's good to understand, to be somebody in the room who is privy to what's going on. Now, last time we spent time deriving and reaching this point, and this is the classic two-beam interference formula, which explains to us perfectly well, once you unwrap this equation, how it is that mixing two laser beams gives us this incredibly exquisite, precise measurement of motion at the surface that you've bounced this laser beam off. And I did make the trip to Irvine. I do have the vibrometer, and I'm going to be able to set it up. And I intend to try to do a demo in here, okay, which will be fun, and then set something up independently in the lab as well. So it is kind of a plug and play device, right? And you don't need to know this theory to know how to use it. It's like DIC. You don't even need to know a lot about DIC to use it. You take pictures, you trust somebody's software, you click some things, and out come a bunch of plots, right? But what I hoped through those exercises that we went through is that when I ask you questions on your report, like, what is the strain radius you're using? What characteristic length does it correspond to? I'm not putting you through some torturous grind. I'm forcing you to realize that these derivatives that you're taking in this software are taken over characteristic lengths on the surface of your specimen. And you should be aware of what that means, okay? That my average mean strains that are being turned into this nice color plot are really being measured over some characteristic gauge length, okay? When you understand that, you're on a level deeper than somebody else who's just trusting what the software is giving them. And what you'll see when you, and those of you who turned it in, I checked all the reports, by the way. I look at all of them. And I look for the value of the stress intensity factor. And you can see that as the strain radius is changed carefully, you do come into that 2.3 value. And if you keep changing it, of course, it'll balloon away, okay? But it does show you that that measure of stress intensity factor is sensitive to the strain radius that you're using in NCORE, okay? I couldn't think of a more vivid example. Yeah, I could go on and on about other things. Let's talk about this now. So what we did was, let me see if I can go back to, I don't know if I've got a picture in the immediate neighborhood here in, what was that all about? Okay. That whole thing just crashed. Okay, let me, we'll report it to them, okay, for whatever that's worth. Okay. Let's come back and open up this file, make sure it's still being shared when it opens up. Andrew, are you there?
I am, yeah, I can still hear you.
Are you seeing it now?
Yes, I can.
Okay, thanks. All right. All right, coming back to full screen mode. So this is what we're talking about. This picture right here. This was last lecture, okay? We're saying when we mix two laser beams by virtue of that beam splitter, we've derived an equation, or I've shown you the derivation of an equation that says, what is the intensity that's going to be reported to a photodetector here when I've superimposed these two laser beams that have come from two different places, one from a test surface of interest, and one is a reference laser beam, which has not gone to the to the test surface, okay? It's just the laser beam that's been extracted from the laser, but by the magic of this beam splitter, we bring these beams together and we control them so that they now go to either a photodetector or a camera. That was the whole idea. And I had to go back and teach you, well, this is how we model a plane wave mathematically, or else you can't begin to model a laser beam. So you're modeling the front of the laser beam like this plane wave, and this is an amplitude, and this has to do with the distance and the direction that it's traveling, and this is time, and this is that ungodly frequency of light on the order of 10 to the 14 hertz, okay? All right, now, once we got past that definition, I had to remind you or teach you what optical phase was. And optical phase, at the end of the day, you should just think of as the 2 pi over lambda times the distance traveled, okay? And what you're doing is you're dividing the wavelength of the light in a formula like this into the physical distance. So it's like saying how many waves of light fit into this distance h, okay? You see? And then this n is just the index of the glass medium. Okay, and then you multiply by 2 pi and you have a measure of radiance. And the reason I taught you this is because interferometers are sensitive to this quantity right here, phase. So what is phase? It's 2 pi over the wavelength of your laser, and then multiplied by the physical distance traversed as it goes through mediums. And when you get to the two beam interference equation, let's get to that now finally. Oh, and by the way, this is where a beam is just reflecting off of a surface, probably the most common application of a vibrometer. Okay, so you're working at a car company and you're worried about the vibrational frequencies of the motor, some portion. You can shoot this laser beam right down onto that motor, reflect back light, and get all the vibrational frequencies present. You can get them on anything that's resonating or vibrating, okay? And you can tune those structures accordingly to quiet down. Yes?
How big can the deflections be? If you put it on the very far end of the beam, if you put it on the very far end, would it be moving too much? Like the cantilever experiment from last class. Like if you put
okay, very good. Very good. So you're saying, you know, where can I put this laser beam? Because if these are grotesque deflections, I'm probably going to just deflect this beam away, and how could it possibly come back? That's right. You want to put it off of a surface that isn't having these large rigid body deflections, so that you can recover this beam back, okay? And there are always opportunities to do that in any good structure, okay? If something is wildly oscillating this much, you don't need a laser vibrometer to know that. You come back here to where it's in a rigid body sense a lot quieter, but all the vibration information is present, okay? That's a very good question, okay? Oh, and by the way, ultimately, like your motion could become so great that it's so much bigger than the wavelength of light that then there are other issues you can encounter with the signal you're generating, but we'll talk about that, okay? Okay, let's move ahead. Let's get back to business. So I'm just kind of going very quickly through to kind of recover the highlights of last lecture. So then this was the magic recipe, which, you know, you would have to take a little bit of time to do, and I choose not to in a class like this. This is the key takeaway here was, read this bullet: cameras and photodetectors respond to the time averaged irradiance. No detector in existence, the human eye to any physical detector, could possibly watch oscillations of light at 10 to the 14 hertz. It's impossible. So what detectors are seeing is this time averaged response. And when you conduct that integral properly and all the steps are missing, the magic recipe that emerges says, and this is the magic of interference right here, it says, if you can give me the electric field representation of the two beams that are mixing and multiply it by their complex conjugate, you will get something that tells you why it is you're seeing an interference pattern in front of you, why it is your detector is oscillating in a sinusoidal way, okay? So we went off and began that journey. We said, okay, well, Any two beams that get combined are called E1 and E2, right? So, by virtue of my beam splitter, once I've finally brought in E1, and here comes E2, and by virtue of my beam splitter, this is E1 plus E2. This is what the beam splitter does for us. It helps us combine these two, right? Now, of course, you threw away a little bit here. Okay, you have to. That's the penalty you pay. 50% of E2 had to be thrown away this way, but 50% got through, you see? And this beam, 50% went through, but 50% reflected. And that's the key, is that these two beams now get to interfere. And your photodetector sits down here, or your camera, and this is what the camera sees. It sees this steady background intensity, which is produced by this one alone. Okay, the steady background intensity would then be just E1 conjugate, and that does nothing for you but just give you a blob of bright light on your screen. Okay, and then there's another piece of the background intensity. Okay, and I gave you the analogy. I said, suppose I just put a sheet of paper here and I block this beam. Okay, then this just goes in, and all you have is that being represented. Or I block this one, and all you get is this one going through, and you get this DC. These don't give you any interference. They just give you background light. Okay, background light beams. If we were in the lab, we'd literally just see a nice circle of green laser light if we blocked one of these beams and let the other one go through. Okay, but when you let them both go through together and they're aligned coaxially, then, and I'll show you what fringe patterns look like, you generate fringe patterns because of these important terms right here. These important terms are the ones that give rise to interference, okay? And so it behooves us to then dive into this one and unwrap this one a little more carefully. So for that, we had to go back to what I told you early on about how to model plane waves, okay? In other words, the only way you ever get to know what E1, E2 conjugate plus, the only way you ever get to know what that plus times that plus that times that are is by actually writing the plane wave, okay, and doing the math. And that's what this slide does. And let's just explode it out and get to the bottom line result, okay? So we modeled the plane waves this way. Notice E to the I stuff. This stuff is the phase. This is the phase information, okay? This has to do with how much the beam is propagated in distance, and this is time. Note something incredible that happens in this recipe. Watch this. Keep your eye on it. Time is here, right? Time is part of the definition of the plane wave, right? E to the I k dot r minus omega t. So isn't it here, right? These are arbitrary phases that we tack on because we know these two beams may have traveled different distances, okay, before they got here. So want to accumulate some additional phase V1, want to accumulate some additional phase V2, we just tack those on, okay? All right, now, here you have to write their conjugates because the recipe asks for EE conjugates. So that's all these are. They have minus signs here. That's it, okay? Minus sign there, minus sign there. We're just sort of setting it up for the machine, right? And now we say, okay, let's clean this up a little bit. Let's call all this phase information sitting in here. Let's just call that psi1, just to keep the terminology light, okay? So we'll just lump all this momentarily and call this psi1. And the same thing with this one. We'll just call this one psi2, okay? It just cleans this up a little bit. And then you begin to multiply this times that conjugate and this times the other one conjugate because the recipe calls for that, okay? This L dot M, this is admitting the possibility that, so when light beams travel through space, they travel this way, but they oscillate perpendicular, okay? So this M and this L are nothing but the directions in space of that oscillation, okay, perpendicular. But we're admitting that when these two beams meet, they might have this dot product between their oscillation directions. They might not be, perfectly oscillating in the same direction, okay? And it says if two beams in space meet that are orthogonal, one is oscillating like this as it travels, and the other one's oscillating like this, 90 degrees away, you'll get no interference, is what this says, okay? You can shut down interference if you interfere two beams that have their polarizations 90 degrees apart, Okay, that's what that dot product reveals. But let's assume that we've made sure that that doesn't happen in our instrument. Okay, and now let's just begin to add up everything because the recipe wants us to report this. Okay, so we multiply everything out, and here's where the magic happens right here. Okay, when you do e to the I C1 minus C2, and then you notice that here you have e to the minus I C1 minus C2, you recognize cosine is lurking, okay? Because you go back to Euler's theorem and you realize you have e to the I theta and e to the minus I theta. All that's missing is the 1/2 under here, right? So if I put a 2 down here and a 2 out here, I now get to bring cosine into this formula, okay? Now, in this conjugate multiplication, I also want you to take note of something interesting that happens, okay? Go back to E1 for a second. Okay, E1 has a minus omega t. You see it? Watch E2 conjugate, right? There's a minus here and a minus here, so that's a plus omega t, right? So what ends up happening is time disappears from the time averaged result, okay? The EE conjugate multiplication assures that time is gone in this. It's a standing wave is what we're seeing. And so time disappears. So when you report this back, time is no longer part of this equation, okay? In the sense of oscillating light fields. Time had to be in the plane wave of the light itself, but the EE conjugate is what gives you the time average result, and time disappears from the equation. So in the end, we recover this magic formula that says mix 2 beams of light, and let's just think of a photodetector first so that we keep life simple. So there's just this little thin beam that we're sending to this photodiode, okay? And out's going to come this electrical signal like that because the light fields E1 and E2 that are interfering are producing something in time that's doing that. Why is it wiggling in time? Because the surface that you reflected the light from is wiggling in time. Okay, this wiggle has nothing to do with the oscillations of light. Okay, these are like your Hertzian measurements in the laboratory, okay, that are causing these wiggles. Okay, and so it says this detector would then report, if this is an oscilloscope, okay, this mean level right here is I1 plus I2. But it's scaled by voltage. So on the oscilloscope, you would call this voltage V1 plus voltage V2, this level right here. You see it? And then the interference part, this cosine, if these quantities are changing in time in your experiment, then you're going to get these wiggles above and below the mean. Okay? I'm looking around and there's very few people focused on what I'm talking about right now. So I don't know if you're just watching something else or what, but this is the magic of interference, okay? This is the 2-beam interference equation, and it is this stuff in here that we're interested in extracting in our measurements. It's this phase information in the argument of this cosine that gives rise to these wiggles in your measurement. And so then we have to say, well, what are these things, phi1 and phi2, okay? And what do you mean K1 minus K2 dot R? So we have to peel that onion and say, what would give rise to these wiggles physically in the measurement, okay? So this figure is just put back to remind you of everything we just did, okay? And it says cases of interest, okay? Let's look at that equation we just derived a few seconds ago and consider cases of interest. Suppose K1 equals K2, okay? So come back to this equation and imagine the propagation vectors. By the way, what those are the propagation vectors are literally like it sounds, right? They're aligned with the direction of travel, right? Each beam has a K, right? If K1 equals K2, that means the beams are perfectly collinear with each other upon interfering. They're perfectly aligned and registered with each other, and this term goes away, okay? So the only reason you're going to get beating now, the only reason this is going to beat is because somehow these two are changing in time, okay? And these are associated with the paths that those beams have traveled. And if one of those beams is traveling longer and shorter distances because the surface it's bouncing off of is changing, then that's why this argument of this cosine is going to start varying. And that's why we're going to have this time varying signal on the oscilloscope screen. Question?
K1, K2 is after they've like hit the glass and been directed, right? It's not like they're in full direction.
No, they're after, because it's the interference problem, right? They're not interfering here. So the interference equation only gets applied when this happens at the beam splitter, right? And we've aligned this beam splitter very precisely and carefully and tuned it so that these beams are collinear and concentric. And if that happens, then this term is not giving rise. Now I'm going to show you what happens when this term is not zero in a few seconds, okay? But let's assume it's zero. Now the only reason this cosine's got any reason to change in time is because the relative path length between these two beams is changing. Question.
The del that's in regards to like small differences in phase angle.
In the optical path length. Okay, so phi was what was defined last term, last quarter. Okay, it's the index times the distance, times the physical distance traveled by each beam. Okay, before they met. Okay, and it's the sum of these NLs. Now, n in air is 1 for all intents and purposes. So, okay, so this is the relative change. So if it's being bounced off two mirrors that aren't moving, okay, and then they're made to interfere and nothing's moving, then these aren't changing either. And you get a stationary pattern in front of you that you stare at and you say, wow, what a pretty fringe pattern. And it maybe kind of goes, comes in and out because of thermal expansions in your optics, and it kind of jiggles a little bit, but it kind of sits there, okay? But if something physically traversed in your experiment and you impacted it, okay, or it was vibrating mechanically, then you'd see that fringe pattern varying in time, and the record of that would be linked to the motion. Question? So see, right. So R is that position vector. You'll see examples when I give specific examples of how R gets used, okay? So in this case, K and R are superimposed. R is the distance vector associated with traversal, okay? So later, we will consider the possibility of them having an angle between them, okay? And you'll see that, okay? K dot R is essentially, in these problems, K times K dotted into the position vector associated with the direction of travel, okay? I will show you an example, and then it'll become clearer to you, okay? So let's now start looking at the cases, okay? So I've already told you this. I've already spent a few minutes telling you this, okay? A stationary interference term, if, you know, depending on whether K equals K2 or not, something's going to arise from this term and some contribution is going to come from this term. And we're going to look at them separately, okay? Here we go. Let's start looking at pictures, because pictures are worth 1,000 words, okay? This is, oh, let me tell you how you expand a laser beam. So right now we keep thinking of these things as a ray of light in this whole derivation, right? But a laser beam is easy to expand. It comes out of a laser with some nominal diameter, and that's reported to you by the laser manufacturer, okay? And in here, there's a nice cavity that the light's bouncing between, and then out comes this beam of light that would slowly diverge over time if you watched it long enough. Okay, it doesn't retain a perfect diameter, okay? But we usually intercept it pretty early on. And if you want to make it larger, so say it has come out with a little diameter D, you could bring in, say, a Keplerian beam expander. And what that does is it forces the beam to focus and diverge like that, because this lens has a focal length f1, right? And then you say, I'm going to pick a second lens, and I'm going to position it here that has a focal length f2, okay? And I'm going to position this lens very carefully so that the two foci meet at the same place, okay? And what's going to happen is your exiting beam now has a new diameter, which we could call capital D, okay? And the new beam diameter is the old beam diameter f2 over f1, okay? That's a beam expander. That's what a beam expander does in a laser optics device. So you could make a fat beam now. And what that means is you could illuminate a surface instead of thinking of like this beam at just like a little point, okay? And so if you reflected it off of the surface and you mixed it with another appropriately scaled laser beam, okay, then what you report, what a CCD camera would see, a color camera in this instance, would see the green light and look at the colored, the dark bands, the zebra stripes that you see, okay? This is two beams interfered, but there's something about their relative orientation that's giving rise to what is called tilt fringes. These are called tilt fringes, and they are associated, they are linked back to the fact that K1 is not equal to K2, okay? They are what give rise to this small tilt angle effect and this parallel fringe effect that the fringes will have. If you then continue to tune in the laboratory and you have access to this beam splitter, if you can eliminate this non-parallelism between K1 and K2, you'll know it when it happens, because a very magical thing occurs. These fringes start to move out, and then you get a bullseye. You get this beautiful circular pattern that emerges, okay? And that circular pattern is just speaking to the concavity of the surface, because that surface isn't perfectly flat, and it's now picking up the shape of the surface, okay? And we'll trace this back to what every one of these individual fringes means quantitatively. We're just not there yet. I just want you to see a demonstration of what tilt looks like. Two tilted beams. These are small angles, by the way. These are not very large angles. You make these angles too large, and the density of this fringes becomes too dense, okay? And you can't see it with your eye, okay? In other words, if you make this very big angle of intersection, the fringes are there, but they're so finely spaced, you can't see it visually, okay? But maybe some other medium might be able to detect it, like photoresist, say, okay? And then you could go develop that photoresist, and you might have like a grating or something back, okay? So this is that case. So let's, and notice in the diagram, I'm deliberately showing that they have a little tilt angle between them, right? So tilt gives rise to what are called tilt fringes, and that came out naturally in the derivation. Now, here are more examples of the tilt fringes, okay, that I just found on the internet, okay? I don't know if you can see those from back here, but they're very, very vertical and straight, okay? And you can rotate these things and have them in various orientations. This one shows you that the surface you're reflecting off of has a dimple, you see? So even though the fringes are revealing tilt, they have a little bend to them because there's a dimpled surface that you're reflecting this beam off of, okay? And that always is going to rear its presence. And then finally, if you would have, this one was tuned beautifully, and I would say such that K1 equals K2, and then you see this beautiful concentric pattern. And the number of fringes you're going to get, these are fringes. Each one of these is a fringe, red to red or black to black, represents a 2 pi transition in that cosine function, okay? So spatially speaking, in that cosine argument, if you were looking along a line, it says the surface height is changing by 2 pi radians equivalent of distance. And every time it does that, the cosine goes through another 2 pi and goes bright, then it goes dark, and it goes bright, and it goes dark, because there's a surface height variation. So think of it as a bowl, okay? Think of it as an arc like that, okay? And the light is reflecting here and mixes with its reference beam, that ray, and then one adjacent to it. But these are at different distances, aren't they? Right? There's a little path difference between those two, right? And every time that path difference changes by the precise amount, according to the sensitivity of the interferometer, a new fringe is registered, okay? So you're getting a topographical map when you look at this surface top-down view. This is literally a topographical map. And if you know how to read this, you can count these fringes literally and say, oh, I know exactly the Z height change that must be taking place from here to there, okay? We can actually interpret that. So that's how shapes are extracted in full field mode. Okay, now let's say we're back to collinear concentric beams. Again, that's what you get. Now, I want to distinguish between a point measurement and a field measurement, okay? The vibrometer I'm going to show you that I borrowed from Polytech is a point measurement device. What that means is the laser beam is focused to a really, really tiny spot on the surface of interest. So all you're measuring when the light comes back is the motion at that location, okay? We're not expanding the beam and looking at a full field view. We're saying, hey, I want to zoom in on a point, reflect light from that point, bring it back, interfere it. In that case, I don't get a picture like this. Okay, in that case, all I get to do is bring light to a photodiode in the device. Okay, and the photodiode is fast and it keeps up with these light changes in intensity. Why do they wiggle? Well, they wiggle because the surface you're bouncing the light off is wiggling. Okay, and so every time it moves by a precise amount, the light intensity goes up and down. Okay, and so this gets turned into a voltage on your oscilloscope screen, and this could be captured and digitized and analyzed. Okay, so that's the idea. You either have full field measurements like this with expanded beams or point-wise measurements, depending on what you're interested in doing. Okay, so this is the example of what I was just alluding to. So let's say this was our laser. We split the beam. We created a stationary reference beam, I1. You see it? It's not going to the specimen. It's going to go from this beam splitter straight down to this beam splitter, and it's going to get split to each of these two detectors. Okay? This beam gets to go through. This lens bounces it and focuses it nicely to a point on the target. Light is reflected, collected appropriately, brought back, mixed, and the interference happens here. The motion of this target is going to induce phase changes that are registered here, according to this cosine. And the oscilloscope screen is going to show you that. So if you set up a single shot experiment and you said, okay, set the oscilloscope to trigger, okay? As soon as the voltage increases by, I mean, if you guys have played with oscilloscopes before, you know you can set a trigger threshold for a single transient event. You can have the oscilloscope watching for a voltage increase, right? As soon as it sees it, it says go, and it digitizes, right? So you could say, okay, I'm going to impact this surface. And you have everything set on single trigger on your oscilloscope. And as soon as the impact comes and the stress waves reach this surface right there, and that surface begins to move, okay, the interferometer now registers this change. The oscilloscope knows that's the trigger, and then you record this event, and you get these wiggles. And then the question is, what do these wiggles mean? How do they translate back to the physical displacement of that target? Okay. All right, so we're almost there. Now we can start to see it. Now I want to unravel for you what's inside the box. This is what slide 1 was when I started this presentation on Wednesday. I said, this is a commercial device called the PDV100 sold by Polytech. And this is what you get as the end user. You get this beautiful little box with a nice lens on the front, and out comes a laser beam, which bounces off your surface and comes back and gets focused back by that lens. However amount of feeble light that comes back is collected by this lens and brought back inside this box. And by some cables out the back, you get all this information I've been talking about, all reduced for you. And you say, wow, that's the surface displacement, that's the velocity. Inside the box is this. When you buy this box for 20-odd thousand bucks, because that's their cheapest model, okay? The cheap model, okay, but it's not bad. This is what's inside that box. It's very close to everything we've been talking about. There's only one mysterious device in this whole thing that we haven't talked about, right? Look, this is the laser. It splits the beam, okay? The beam goes, ignore this guy for a second. The beam goes straight through, goes through that base filter, goes to our target. That's our surface that we're interested in measuring. That target scatters some light back. It gets reflected here, brought to that diode. Meanwhile, some of the beam, which is the reference beam, went up and through, and we get our two beam interference here, okay? So here's the, you know how you get ambiguities in measurements? Here's the classic ambiguity you get with interference. If somebody gave you, let's go to the full field analogy for a second. If I said, here's my my fringe pattern, okay? And I say to you, that represents the surface profile, but a top-down view of a contour map. You have every right to say, is the center high or is the center low? Right? Is that a mountain or is that a crater? Right? And I'm here to tell you that if somebody just presents you with a single fringe pattern, the answer is you don't know. You have no way of knowing. It's completely ambiguous. It's like, I don't know. How would I know? You have to do something when you're making the measurement to be able to resolve that and explain that back to the end receiver of the information. Okay? Because all that is if I gave you a topo map, and I just said, here are the circles, you wouldn't know, are you giving me a hill that I'm going to climb over here in Altadena, or is this a crater that I'm walking down, right? I have to tell you the elevation increases as I go this way or decreases as I go this way. So that's what this Bragg cell does. This Bragg cell helps that be resolved. And the end user is oblivious to this. It's beautiful. The Bragg cell, you can Google and Wikipedia Bragg cell, okay? Can't dive too much into this. It's a crystal, and has this resonance vibration that sets up an index of refraction variation inside. And you can put a frequency onto this beam even before it gets to your target. And it's associated with something, that Bragg cell, it's about 40 megahertz, okay? So the Bragg cell puts this 40 megahertz frequency onto this beam even before it gets to your target, okay? So then your target is spitting back the fundamental frequency of the light itself, the Bragg frequency that this Bragg cell put on it, and then FD for Doppler, okay? Meaning the motion associated with this target. I don't like to use of the word Doppler, and I will explain that later. But these are the three fundamental frequency components that come back, and then the one that only went this way is F naught, okay? F naught's the only one that went this way because it's the fundamental laser beam. And then this subtracts, and you're left with, as an output signal, F Bragg plus F associated with your target, okay? So let's say your target's not moving. Let's pretend the target is perfectly still. I'll bring you guys back if I just lost you, okay? Target we imagine to be perfectly still for a moment, okay? And we send light through this Bragg cell, and it puts 40 megahertz frequency on this beam, okay? So when we mix and we do the interference, FD is 0 because the target's not moving. So this interference problem ends up subtracting these two. So the F0s go away, and all we see is the Bragg frequency that this cell put on the signal. So our oscilloscope screen, even if the thing's not moving, would give us this beautiful 40 megahertz signal. And if we took an FFT, we'd see this sharp spike at 40 megahertz, okay? Even if nothing's happening. This is the magic of what this device is doing, because now, if your surface moves away or toward, okay, it's going to either increase this frequency or decrease this frequency, okay? When you actually let the thing move, the frequencies you're going to register are either going to be below this or above this. So because we know this baseline, depending on what side we are, we know if this target is moving this way or that way. Yep.
It's a very
okay.
realistic question, but what if the target moves at that specific frequency? Like, because like we kind of don't sometimes we don't have like.
So yeah, that's good. That's good. So the answer is you design the device for applications that will not happen, okay? And so they've chosen that 40 megahertz to be deliberately far from what would happen in the measurement, okay? So think of these as small perturbations, but measurable perturbations to either side. And the FFT can see that. And all this gets done in real time. So this is called heterodyning. If you ever hear this term, it sounds complicated, but heterodyning is the technique of introducing deliberately a frequency to your signal that is there even if the thing's not moving. And by knowing what side you're on, you've resolved the direction you're moving. That's very beautiful. In the lab, if you did this one, this is a very interesting one, and I've done this myself. If you're doing this and you perturb the sample, okay, if you perturb the sample in a particular way, if it's convex, the fringes will radiate out as you perturb the sample. If it's concave, they'll radiate in, and that can be resolved by going through the derivations. So you can actually do physical perturbations of the specimen, and if you watch on the screen, the fringes tend to radiate in, radiate out for a known movement of this surface, then you've resolved in the lab whether it's convex or concave. These are all some mini deep dives. All I'm trying to do is, the message here is we could make half the lecture this heterodyning thing. I'm just trying to give you the big picture that a commercial device has to be able to reconcile this for you, okay? And so a successful device has this Bragg cell signal. Yep.
Does Bragg frequency also introduce interference with the original frequency?
No, not anything that would be registered in the measurement. Okay, because the two beam interference. Okay, so this is a cartoon which fails a little bit. Okay, but I'm going to explain. The two beam interference takes away the omega of the light. So when you go back to the two beam interference equation we saw, everything time-based in the plane wave description disappears. So I've been waving my hands here saying F naught here minus this F naught go away, okay, in this cartoon. They go away because of the two beam interference problem, okay? See, I'm just saying this comes back because they haven't mixed yet. This comes in with F naught. And if you do the two beam interference calculation, the time average solution says the original frequency of the light, 10 to the 14 hertz, this ungodly frequency, that disappears in the time. That's what time averaging is. No detector could follow that. Okay, so I should add something to this cartoon that says output from here, this gets naturally subtracted from the time average process. Okay, so no, it wouldn't do anything. Okay, all right. Now, this is just one playing around with the equation to show why these vibrometers are reported to measure velocity. Okay, if you go back to the phase that the vibrometer is registering, you have 2 pi, here's the Bragg frequency. This is time now in the measurement time, okay? And then this is displacement of your surface, UI, normal displacement. And this is some characteristic time over which you're measuring, okay, delta t. And so what you do here is, if you look at this line, the delta t wasn't here. So I've multiplied and divided by delta t when I went from this line to this line, okay? And by doing that, you identify, oh, if this delta t in your measurement window is small enough, we can consider this to be the displacement at time t plus delta t minus t divided. This is the velocity. So no instrument really measures velocity, okay? These devices really measure displacement, okay? But if you say, okay, but over these small enough times that I'm doing these local averages over, I can estimate these as good velocity estimates. But the interferometer equation never spoke of velocity. It was only when we decided to multiply by delta t over delta t here, okay, that we rigged velocity to come out of the description. But this is an output of the device, okay? So you can select velocity and it will give you information associated with velocity. Oh, here, this is very good. Let's continue talking about that. So I want to get back to the Bragg signal. So finally, the instantaneous angular frequency that you get from this vibrometer, okay, when I'm talking about that frequency, I mean the frequency you're measuring on your oscilloscope, okay? Don't confuse the word frequency with other things. The frequency of the signal that is output says I've got the Bragg in me, FB, and then minus the velocity of the surface you're measuring, okay? And so there's the difference between the two, and that difference is either going to be a frequency that's registered to the right or left of FB, right? If the velocity is 0, my interferometer reports this FB, 2 pi FB, right? If my surface is moving, I'm reporting differences, and this velocity U dot multiplied by these appropriate numbers is a frequency, okay? So it is that delta that is being registered, and that's why the interferometer, the device, can tell you, yeah, it moved forward, it moved backward, it went back and forth between some place. It's completely resolved. Now, in the business, they call this the Doppler frequency shift, and that bothers me because if you go back to your physics and you really read what Doppler frequency is, okay, it is not this. But this is what happens in the commercial world. Once the cows are out of the barn and they've called something this and they've written it all over their website and in their product brochures, and they decide we're going to call this the Doppler shift, okay, there's no reining it in anymore, okay? So an intelligent engineer who knows this stuff understands it, but it's like, bugs me, okay? Because if you think about what the Doppler shift is, yeah, it's analogous to it, but this is not what we're doing here, okay? This is the thing that is being measured, though, okay? You're measuring the velocity, the frequency Doppler, they call it. They're calling this piece FD, okay? They're calling this frequency Doppler, okay? All right, that's okay. Now, I have other cool things that I want to show you. There's lots of nice video links in here. This is something I did in the lab in downstairs, and I could even do this with you guys this year. Just I opened up the presentation with this on Wednesday. So here's a laser vibration. Is this the movie? I guess this isn't the movie, but I showed you the movie as I panned around and showed you what was going on. Here's the vibrometer focused way down here. This is retroreflective tape that really helps a lot. It's if you look at what retroreflective tape is under a microscope, you'd see a field of little tiny glass spheres. Okay. Very, very tiny microscopic glass spheres. And it comes with an adhesive backing. So if you stick it on a surface, it scatters the light back wonderfully. An efficient scattering of the light comes right back into the vibrometer. So it really aids in getting more photons or more light back into the device. Okay. And then this is the rigging of this beam that was registered by this vibrometer. Okay. We just kept flicking it. Okay. And it would damp out. So we tell the vibrometer to record, and notice what you get, sent out to you is immediately this amplitude versus time, okay? Right? It's already processing all this information for you. Okay. Now, got a few minutes left, and I want to talk about, oh yeah, that's what the instrument might look like. So you, the end user, might never know what the heck's inside here. And the optics are in this box, okay? The beam splitter, the mirror, the Bragg cell, everything's in that box. And they sell it to you with this beautiful fiber optic, so that you can imagine you're in industrial environment, you're going to snake this fiber somewhere and position it and collect light off of some difficult to access location on your engine, say, of your automobile, right? So this will send the light and collect it, send it back in. All the mixing happens in there, like we've been talking, and out through this box, which does all the conversions for you. Then this will kick out of the velocity or displacement BNC connector to the oscilloscope, and you'll get an immediate velocity or displacement versus time. You don't have to do the data reduction. You're paying tens of thousands for this firmware and software to take that interference signal from the detector, interpret it, and then output to you velocity versus time. That's what you'll see when I demonstrate it to you. We won't see these fringes. Nobody gets to see these, okay? They're inside the box. What you'll see is the output, okay, which has been processed. I want to see if I could find, the rest is just nice applications of interferometry, but I wanted to show you how we measure the sensitivity of the interferometer in the most basic problem. Let me just kind of wing it and show you by just writing something on the board. I want to go back to way back in the beginning when I showed light bouncing off of a surface and we talked about phase. Let me go back and find that now. Give me 1 sec. Here we go. This one. Okay. We opened up this conversation on Wednesday by me showing you, this is good to retreat now and go back in time. I felt like the only way to whet the appetite, so to speak, to say, what does an interferometer do? Okay, what does it measure? Is to try to impress on you, without showing you the two beam interference calculation first, that it is optical phase change that interferometers report, okay? And this is a very easy one to imagine. This mirror was here at time t1. It shifted forward to this position by delta at time t2. Okay, so the path length changed by delta. So this laser beam that came in, okay, it reflected off of this thing when it was here, and later it's reflecting off it when it's here, right? And so the path length is delta, but the beam traverses it twice, right? 1, 2, right? In, out. You say, wow, wait a minute, how can you do that? Because the surface is moving, right? But light travels at 3 × 10⁸ meters per second. So for every delta, that light beam gets to go, boom, boom, I've sampled you, right? Give me another delta, boom, boom, I've sampled you, your history. I'm at 3 × 10⁸ meters per second. What are you, okay? So it reports this phase change back to the interferometer. The interferometer picks up, okay, a phase change, the cosine term, all it has in it, these are the DC terms, okay? 2 square root I1, I2 is the amplitude portion, cosine delta phi, okay? And that delta phi is really cosine of 4 pi over lambda naught in this simple interferometer that I'm presenting to you. Oh, let's say delta is of t, because it's moving. The mirror is moving, right? So this is just the amplitude of the cosine, okay? Okay. By the way, when I say I here, you can think of this as voltage, because intensity to the diode becomes voltage to the oscilloscope, 1-to-1. Okay, so as long as the oscilloscope's fast enough. If the oscilloscope has the bandwidth, and you've paid money for that bandwidth, it'll keep up with your diode, right? And then it'll say, okay, I'm going to report. So you could make these V's if you want, and imagine a voltage on a screen now doing this that you've recorded as this surface moves. And this is the perfect last thing to tell you. So just check this out. If you say, how do I know how sensitive this device is? What's a good way of gauging how sensitive this device is? Well, you say, all right, what does it take? What does it take for delta phi to go through 2 pi, right? Because every time delta phi changes by 2 pi, what happens to this output? This output goes on my oscilloscope screen, goes like this, okay? Comes back to where it started, right? Every single time the phase changes by 2 pi, this thing goes through a period on your oscilloscope screen, right? That's what's literally happening here. So you say, okay, this is interesting. So I'm going to say 2 pi is equal to 4 pi over lambda naught delta of t. And the pi's cancel, and then you get delta of t must have moved by that amount. Remember what this number is? It's the wavelength of light. Let's pretend we're using a helium neon laser. It'd be 633 nanometer, okay? Or 633 times 10 to the minus 6 millimeter, right? But let's just leave it in nanometers, just in case I got my powers of 10 wrong there, okay? Think about that. It says every single time this mirror moved by half a wavelength of light in here, 2 pi was registered again in the cosine. Do you follow that? So on your oscilloscope screen, you literally now have a conversion. It says this 2 pi change is equivalent to my surface moved by half a wavelength of light. Do you realize that's how sensitive an interferometer is? It can measure half wavelength of light motion, okay? So it gets back to your earlier question, like what could happen in a measurement? Well, your surface is moving so fast that the frequency you register is so high, okay? Because remember, every time it goes through lambda over 2, another fringe is formed, right? And this is an electronic fringe, right? This is what we mean, this is time on the oscilloscope, right? So we would call this an electronic fringe. This is voltage, right? Okay. So my point is, you could have a surface moving so fast that your detector can't keep up with the interferometer signal at some point, right? So again, it always gets back to this thing I've told you guys about the speed of devices when you're speccing them. You have to say, what am I anticipating measuring? Is my diode fast enough? Is my oscilloscope fast enough? Do they work together, even though they're going to convolve my signal? Do I get a faithful replica of what was happening? And as long as the bandwidth of the instrumentation is high enough, you will follow it. That's the most exquisite demonstration of how sensitive interferometers are. The last picture I'm going to show you, because I'm going to start a new topic. I know I've gone over, but you have to see this beautiful image, and then I promise I'll stop. I want to go to the last slide. Okay, I'm just going to purposely go here to say this is the king of them all. Okay, these people have my respect. Okay, this is crazy what these people have achieved. Okay, this is beyond crazy. I've spent my whole life studying interferometers. I've written papers on interferometers. I'm known in my little community for this business, and I still am staggered by what these people have done. It is obscene. Okay, they're measuring a strain change of space of 10 to the minus 20. Okay. It's incredible what they have, the lengths they've got. This is an interferometer. This is a 2-beam interferometer, by the way. It's just a very fancy one. Okay, there's a really special beam splitter in here. Okay, there's a mirror way down here, 4 kilometers away. there's another mirror over there, 4 kilometers away, and they go two beam interference, right? But in a very, very fancy way, okay? Wham, and back, okay? And if a gravitational wave sweeps through and changes the relative path length between those two interfering beams, something got registered, and everybody jumps up and down. And they go, what did the people in Washington see? Did they see the exact same thing at the same time? And if they say, what did the people in Italy at Virgo see? And if they get all these three sites seeing this little ripple at the same time, they jump up and down. And that's another detection of a gravitational wave because they ruled out every other possibility. But the lengths they have had to go through to quiet this thing down, literally in Louisiana, like the water coming up on the ocean, okay, is being registered with this thing, okay? They can pick up all the noise in the earth with vibrations that are messing with this thing constantly, right? And so the triumph of the people who worked on this, and it's a huge list of people, okay? If you look at the paper, it's ridiculous, the list of people, the authors, okay? Because people conquered how to quiet and suppress all the vibration noise sources in the world that could corrupt that measurement, okay? And they get it so quiet within a certain bandwidth, they could measure the stretch of space-time, okay, as it perturbs the relative length of these two interferometers. It's almost not believable, okay, at first glance, right? It's almost not believable, okay? But the lengths they've gone through to prove it are incredible. And this, by the way, this is their measurement. There it is. Those are the wiggles. Those are the same wiggles we've been talking about. And they go, look, those guys got it, and those guys got it, and we all got the same thing, okay? It's cool. I'll see you guys next week.